So this is thought to be where the elements that make our bodies come from. So there's actually a kind of a cycle of life going on. You have these clouds of gas, and then some stars explode. The dying stars squirt out this enriched gas with all the nice yummy heavy elements in it. This gas then collects into new stars which form over here. New stars in turn explode and squirt out even more gas, and so on and so forth, a constant recycling. You also get new gas from the Big Bang raining down at all stages. That's the next puzzle. We end up with a spinning disk of dust and gas around a newborn star like this. This is what happened in our own sun about 4 billion years ago. Now in this disk of gas, all the heavy elements start sticking together. There's a force called the van der Waals force you may have heard about in chemistry class, which can cause these little tiny grains of solid material to stick together and form slightly bigger grains like you're seeing over here. Maybe icy grains in the outer part where it's cool and rocky grains in the inner part. And it's out of these tiny grains, too small for the eye to see, that we think planets form. The next stage is what I like to call the era of carnage. I'd like to show you a computer simulation of this. What I've done in the simulation is put a whole bunch of small planets. What I've done in the simulation is simulate this. I've put a few hundred of these things in random positions, and we can see what happens as they orbit around. So here we go, the sun in the middle, and we start with lots of these small things in random positions. And what you'll see is they start to affect each other. We can rotate the simulation, look at it from different angles. Now this is a story that actually starts quite a long time ago. It starts back in the 19th century with the discovery of spectroscopy. This was an incredibly useful thing discovered by 19th century physicists. And that will give you a graph that looks something like this, showing you the amount of energy against wavelengths. It's the blue wavelengths, the red wavelengths, not much energy down the bottom, lots of energy up the top. In the 1920s, telescopes became powerful enough to measure spectrum not just for nearby galaxies, but for faraway ones. And they looked something like this. So it's got bumps and wiggles all right, but they're not in the right place. So let me show you a simulation of this. So here, we've got spheres as proxies for galaxies, and you can see they're all steadily moving apart. They're not actually doing anything, they're just sitting there. What's happening is the space between them is growing. It doesn't matter what orientation you look at them from. You can look at them from down here or up there, and you'll see, so they've moved out, the gravity slowed them down, and now it's coming back together again. You can see the same from any orientation. And things are getting much denser. In this case, everything will have redshifts, and they're actually rushing towards one another. I stopped it here where everything's crammed together. That's because my code couldn't manage it any further. In principle, they keep on crushing all the way down to get to a point. But let's see what's going on here. What we know is at the moment, the size of the universe is getting bigger. So the universe is smaller in the past, bigger in the future. The question is, if we extrapolate that forward, what's going to happen? It could be that the universe keeps on expanding forever, in which case in the past it would have been going at a fairly steady rate. An alternative would be that the universe is going to go a bit slower, get a maximum size, and then come back down to some horrible big crash.